All right, let's start right here.
What is quantum computing?
Yeah. So it's a proposal for a new type of computation, or let's say a new way to harness nature to do computation that is based on the principles of quantum mechanics.
The problem with that statement is that quantum mechanics does not describe nature. It can't harness the power of nature because it is a pseudoscience. Now, most people tune out right here because they think that quantum mechanics is our best working theory. But what most people misunderstand is that we're actually using Schrodinger's wave mechanics and not quantum mechanics. And this is not my theory. Wave mechanics and quantum mechanics both use the same math, but quantum mechanics applies the complete opposite meaning to the Schrodinger wave equation. Okay, let me show you what I'm talking about. In 1933, Erwin Schrodinger won a Nobel Prize for the discovery of a new productive form of atomic theory. His Nobel lecture was on wave mechanics and not quantum mechanics. Now, Werner Heisenberg also gave a Nobel Prize speech the day prior because his prize was delayed by 1 year. He was one of the founders of quantum mechanics, and that is exactly what his speech was about. Now, back to wave mechanics. Schrodinger described quantum mechanics as point mechanics, or point particle mechanics, which differentiates it from his wave mechanics. This idea just doesn't seem to get taught. Instead, wave mechanics is just the equation used in quantum physics. But really, wave mechanics is more than that. It's the actual competitor to quantum mechanics. The point particles of quantum mechanics collide in a completely different manner than when waves collide with each other. This type of interference pattern is created during wave collisions. So how can a wave-based physics and a point-based physics both be using a wave equation to describe nature? Okay, let's continue.
Okay, so what does quantum mechanics say about the world? The physicists, I think, over the generations, convinced people that that is an unbelievably complicated question and, just give up on trying to understand it.
A quick suggestion. Don't fall for this line by physicists saying that you're not going to be able to understand this stuff. Modern physics has made some very fundamental errors that adds to this idea of complexity and confusion. You don't have to believe me about this. You can test this out yourself.
I can let you in, not being a physicist, I can let you in on a secret, which is that it becomes a lot simpler if you do what we do in quantum information theory and sort of take the physics out of it.
You have to be careful with this because now you're taking a leap of faith and believing that the physicists are correct.
So the way that we think about quantum mechanics is sort of as a generalization of the rules of probability themselves.
So at this point, computer scientists would be jumping straight into the math. Instead, let's take a look at a common fairy tale that is told about quantum physics.
Molecules, atoms and molecules, they operate using the laws of quantum mechanics, or by the laws of quantum mechanics. Us here have different sets of fundamental laws that allows us to kind of predict what we do, classical mechanics. And quantum mechanics and classical mechanics are very different.
Okay, so let's debunk this idea that we need a specialized physics for the small worlds of molecules and atoms. We are going to look at Schrodinger's 4 lectures on wave mechanics from March 1928. He discusses this topic in the first lecture. Ordinary mechanics is only an approximation which no longer holds for very small systems. But Schrodinger's description is different than what quantum mechanics says. Ordinary mechanics, or classical mechanics, treats many things as projectile paths and mass points. This would be just like the idea of calculating a baseball flying through the air. And specifically, when you are describing light in terms of a ray, which is like a straight line path, it becomes just an approximation and can work in the world of the big. But when things get really small, like within the atom, treating light with the ray method is of no use. So wave mechanics is what is necessary in the world of molecules and atoms. But here's the kicker. Wave mechanics still uses classical wave physics. Basically, he is saying that the requirement for the atomic world is to use waves. And the quantum theory guys were using mass points like electrons and photons and paths like electrons orbiting around a nucleus. So the big difference here is how Schrodinger treated the electron. Quantum theory treated the electron as a particle moving along a path, and Schrodinger treated the electron as vibrational waves of a field of negative charge. And by waving this electron medium, he is able to explain what we observe experimentally about atoms, and it's consistent with the classical electrodynamics of Maxwell. So just think about what Schrodinger did here. He just made quantum theory obsolete because his wave equation describes the atomic experiments. And he does this using classical physics. Okay, so here is a question for you. If Schrodinger reunified physics with the wave idea and the wave equation to prove all of the observables of the atom, wouldn't you think that Schrodinger's wave mechanics would deserve its own section on Wikipedia? I mean, at least get its own section on Wikipedia? Or maybe see some of Schrodinger's ideas in the mainstream physics videos. Instead, it seems to just get shuffled under quantum mechanics and quantum physics, which still keeps physics separated. And many times you might hear that Schrodinger's cat is a thought experiment that helps explain the Copenhagen interpretation of quantum mechanics. This is Schrodinger's 1935 paper where the actual Schrodinger's cat paradox comes from. Now, as I just showed you, Schrodinger has already explained away the need for any of these quantum mechanics or quantum theory type of explanations in physics. But they still persist, and Schrodinger is making fun of how quantum mechanics is using his wave mechanics equation. So using quantum mechanics, one can even set up quite ridiculous cases. And Schrodinger's cat is just one of those cases that he was describing to help you understand why quantum mechanics is ridiculous. So maybe something was lost in translation, but it seems like ludicrous would have been a stronger translation of this German word. And it's crazy to think that the popularity of Schrodinger's cat, it's just one little paragraph in this paper. I'd like to continue on with the current state of quantum computing. But if you don't understand what separated quantum physics from classical physics, you might be thinking that it's just one person's word against another. So I need to quickly run through what made quantum physics a separated physics. The separation of quantum physics from classical physics really gained steam with the introduction of the Bohr atomic model. In 1913, Niels Bohr introduced his model of the atom, and his idea was that classical physics or classical electrodynamics was inadequate for describing the behavior of a system of atomic size. He based this idea on a previous atomic model that failed. And remember that Schrodinger's model of the atom uses classical or ordinary electrodynamics, which is the opposite of what Niels Bohr is saying. This is the first assumption that Niels makes that splits quantum physics from classical physics. It's the idea that the electron can orbit the nucleus but not radiate any energy. Since classical physics would not allow that to happen, he is going to file that assumption into this new physics called quantum physics. And these new quantum orbits are called stationary states. Now take this assumption of the stationary state and transition between these different stationary states. You get another feature of quantum physics that cannot be explained by classical physics. This is commonly known as the electron jumping between orbits, or a quantum leap. And this orbiting electron takes no time to jump through space. Let's look at this PHET simulation of the Bohr atomic model. The electron is orbiting in the non-radiating stationary state of quantum physics, because classical physics would not allow this kind of perpetual motion to take place. Now, when we turn on the light source of white light, it is going to send particles of light at this hydrogen atom. When this electron particle gets hit by a light particle, it will jump orbits just like it did right there. This electron jump or quantum leap is another example of why quantum physics split from classical physics. So how do we know that any of these atomic model ideas have any validity at all? You use math to describe the ideas, and those answers should be pretty close to what we experimentally observe. And the Bohr model of the atom did a pretty good job at doing this. Let me give you a real quick example of how we would experimentally observe atoms. I will use the line spectra of hydrogen as my example. So you would electrify this tube that has hydrogen gas, and it's almost like a fluorescent lamp. You use a spectrometer tool to view this gas, and it gives you these bright bands. Each atom has a unique set of these bands of color called line spectra. And these are the unique spectral lines for hydrogen. Now, the math for the atomic model should properly predict each of these bands of color, and maybe even the brightness or intensity of the color. Also, how they are affected by strong magnetic or electric fields. So the Bohr model got some of this stuff right, but he had to use those non-classical assumptions that we now call quantum physics. Now, going back to Schrodinger's wave mechanics, his wave-based math was in complete agreement with these experiments. But there is a very major difference here. Schrodinger explained the atom without using the quantum conditions of stationary states or jumping electrons. In fact, he got rid of the electron particle itself and the orbital path that went around the nucleus. So now do you see how Erwin Schrodinger reunified physics by getting rid of the need of those quantum physics assumptions? Why doesn't wave mechanics get the publicity? And why do you always see Schrodinger's work get combined with its competitor? So the last part of this story has to do with Werner Heisenberg and how we transition from quantum physics to quantum mechanics. And in 1926, Schrodinger writes this paper that shows that his wave mechanics and Heisenberg's matrix mechanics, or quantum mechanics, are getting the same answers. And remember that Schrodinger said that these quantum particles and their paths will not work in the world of the small. So how are they getting the same answers? And then we have to figure out the real difference between Schrodinger's wave mechanics and quantum mechanics.
Schrodinger hated what Max Born said. Einstein hated it. But never mind, Max Born was right. Max Born said it represents probabilities.
So why exactly was Max Born right and Schrodinger was wrong?
Schrodinger cat experiment was a way of Schrodinger to try to say how ridiculous the probability interpretation was. Of course, it's not ridiculous, it's right, and
in the next video, we will continue to understand why quantum mechanics is a pseudoscience, and we'll return to talking about the current state of quantum computing.